Welcome to Sporty's What You Should Know About Transitioning to Gliders. This program takes you into the realm of unpowered flight and introduces the art and science of soaring. Along the way, you'll be treated to insights from some of aviation's noted authorities, Flying Magazine's Richard L. Collins, and soaring expert and author Bob Wonder. Your host is Rob Ryder. An instrument-rated pilot and real aviation enthusiast, Rob serves as an announcer for various air shows and hosts many other Sporty's video programs.
Hi, thanks for joining us. In this program, we're going to teach you what you should know about transitioning to gliders from powered airplane flight. We'll cover glider aerodynamics, rules, launch methods, soaring, special equipment, and more. Your instructor may do things in a slightly different manner when approaching the same information. That's okay. Having different perspectives on the same information will benefit you as a pilot. If you're not an airplane pilot already, or are a bit rusty, you should review the basics on Sporty's Private Pilot DVD course. The trainer we use here at Sporty's Academy is the Diamond Extreme Motor Glider, model HK36TC. It is self-launching and has a 27-to-1 glide ratio. Even though it has an engine, this aircraft is certified as a glider, and that means you must have a glider rating or a self-launch solo endorsement in order to fly it. To fly a glider, you must be able to attest to your own good health, but you do not need a medical certificate. To carry passengers, you must have a glider rating on your pilot certificate. The FAA requirements for adding a glider rating are listed in Part 61 of the regulations. You do not need to take a written test for an add-on rating if you already have a private airplane pilot certificate. You do need to pass an oral and flight exam with an FAA inspector or designated glider examiner. A pilot needs to be only 14 years old to solo in a glider and 16 years old to earn a private pilot rating with glider privileges. To add a glider rating to your private certificate, you need only 3 hours of glider time if you already have 40 hours of flight time in heavier-than-air aircraft. Your glider time must include at least 10 solo flights. 3 of the training flights with your instructor must be in preparation for the practical test and within 60 days prior to the test. A flight is generally defined as a launch, trip around the pattern, and a landing. The rating added to your pilot certificate will be for a glider. An instructor will endorse your logbook for one or more of 3 possible launch methods. A self-launched glider has an engine to power it into the air, which is shut off for soaring flight. The propeller may be designed to feather, allowing the propeller blades to be streamlined into the wind, or the blades may tuck away into the nose of the glider. Other designs stow the entire motor and propeller assembly in the fuselage. The self-launched glider can be a good way for power pilots to transition to soaring flight. It allows you to take more of what you have learned in airplanes into the glider cockpit. The aerotow is the most common launch method in the United States. Aerotow is an airplane pulling the glider into the air. The glider pilot then releases his end of the tow rope and turns away from the airplane. The third launch method is the ground tow, using either an automobile or a winch on the ground to pull the glider into the sky. Bungee cord systems were used in the past. The ground tow method requires a long cable or rope. The length determines the maximum release altitude. While somewhat limiting in altitude, the ground tow method can be the most economical. While they may look similar, gliders and motor gliders are different than airplanes. The rules for certification are different, and quite often the feel of the controls is different. Aside from the presence or absence of a motor, which differentiates non-powered gliders, one very noticeable external difference is the length and aspect ratio of the wings. These long wings make for a significant change in the flight characteristics compared to an airplane. Pre-flight of the glider also has some differences. Gliders are often disassembled and trailered to the airport. Once unloaded from the trailer, the wings and flight controls have to be reconnected. This does not require an airframe maintenance certificate. Your critical assembly checklist after assembly must include a positive control check. This requires the assistance of a knowledgeable person to apply pressure to the control surfaces while you manipulate the flight controls. For non-powered gliders, you may also need to assist in the pre-flight of other equipment, such as the tow rope or cable. While this may be considered the tow pilot or winch operator's responsibility, you have a vested interest to ensure that the line is acceptable. The line should be in good condition and free from knots. Knots decrease the strength of a tow rope by up to 50%. Splices should be secure, and the tow ring should be the correct type for your tow hook. A tow line used in aerotow must have a braking strength between 80% and 200% of the maximum certified operating weight of the glider being towed. If the rope is stronger than this, safety or weak links meeting the 80% to 200% criteria must be installed at each end of the tow rope. The weak link at the tow plane end of the rope must be stronger than the other safety link, but not more than 25% stronger. Winches typically use a cable instead of a rope. A cable should have a safety link installed at the glider attachment point. This weak link should be from 100% to 200% of the maximum certified operating weight of the glider. Like an airplane, the glider must have the appropriate certificates and documents on board. The standard Aero works here. If you're flying a motor glider, you will see a number of familiar engine instruments and controls. The operation of these controls may be conventional, but don't take this for granted. The Extreme is equipped with a constant speed propeller. Unlike most single-engine airplanes, the propeller control has a position for feathering. The Extreme does not have a mixture control, so the engine is turned off using the ignition switch. Other motor gliders have controls for retracting the engine or closing the nose after propeller retraction. Primary flight controls for the pitch, roll, and yaw of a glider are very similar to an airplane, but don't expect to jump right in and be perfectly coordinated. The long wings of the glider have more adverse yaw than airplanes. Secondary flight controls may be different from what you are currently using. While some gliders use traditional trim tabs, trim in the Extreme is set through spring loading on the stick. The flaps on a glider may be of the same designs as found on an airplane. Some flaps can be deflected slightly upward. This is called a negative flap and allows the glider to fly at a more efficient angle of attack with lower drag at higher airspeeds. Downward deflected flaps generally lower the stall speed of the aircraft while increasing drag. Some gliders, including the Extreme, do not have flaps. Spoilers, dive brakes, or slips are used to control the angle of descent. Spoilers generally deploy from the top of the wing and disrupt or spoil the lift. This also creates drag. Dive brakes typically deploy from both the top and bottom of the wing, both spoiling the lift and significantly increasing the drag. Spoilers and dive brakes raise the stall speed of the aircraft and transfer flight loads to other parts of the wing. Other gliders use a high drag device, such as a drogue chute, to increase the angle of descent. While very effective, this type of device may not be reclosable in flight. The drogue chute does not change the stall speed. Most sailplanes don't have gyroscopic instruments. Some, like our Extreme, do. The Extreme's gyros are electrically driven. There is no vacuum system. Gliders do not have a standard vertical speed indicator like those found in an airplane. Instead, a more sensitive instrument called a variometer is used. This instrument may be mechanical or electronic and will be covered in detail later in the program. An unusual instrument found on most gliders is very simple in operation. It's the yaw string. The yaw string is attached to the canopy at one end so that it will streamline with the airflow over the aircraft. In coordinated flight, the yaw string will flow straight back. When uncoordinated flight occurs, the air flowing over the aircraft comes from one side or the other. This causes the yaw string to deflect to one side. To resume coordinated flight, apply rudder on the side opposite of the string's deflection. In other words, step on the tape or step on the string's anchor. The glider may also have an inclinometer. It works the same as in an airplane. When the ball is off center, step on the ball.
If you learn to fly a glider using one of the towed methods, there are a number of signals that you must understand to communicate with the tow pilot and ground personnel. We'll start with a review of the signals commonly used for aerotow. On the ground, a crew member will signal the sailplane pilot to check the controls by rotating a thumbs-up signal in a circle, to open the tow hitch with an open hand, and to close the tow hitch by closing the hand. A crew member will signal the tow pilot to take up the slack in the tow rope by moving an arm from side to side, and to hold position by holding both arms out to the side. The glider pilot will signal the crew member that he's ready and wants the wings leveled with a thumbs up. Begin takeoff may be signaled by the sailplane pilot by waggling the rudder. It may also be signaled by the crew member using a circular motion of the arm. The crew member may signal the tow pilot to stop the engine and release the tow line by moving the hand back and forth across the throat in a cut motion. An emergency or other factor that requires the operation to stop can be signaled by the ground crew member by waving the arms above the head. The glider pilot can send this same signal by initiating a tow release. Once in the air, the sailplane pilot will signal the tow pilot by movements of the glider. To request a turn to the right, the sailplane pilot maneuvers to the left and gently pulls the tail of the tow plane in that direction. A turn to the left is requested by going to the right. A desire to increase the tow speed is demonstrated by rocking the wings of the sailplane. Decreased speed is requested by wagging the tail of the glider using the rudder. These are performed directly behind the tow plane. If the tow pilot needs the glider to release immediately, this will be signaled by rocking the wings of the tow plane. To signal the inability to release, the glider pilot should move out to the left side of the towing aircraft and rock the wings of the glider. The tow pilot would signal the inability to release by moving the tail of the tow plane from side to side with the rudder. To warn the glider pilot that spoilers are deployed, the tow pilot would fan the rudder rapidly back and forth without yawing the tow plane significantly. Ground tow procedures use many of the same signals with a few differences. A crew member holding the glider wing down on the ground signals the driver or winch operator that the pilot is not ready. The signal to take up slack is provided by the crew member raising and lowering the tip of the glider wing. This should only be done when the glider pilot is ready for takeoff, as taking up slack in a long cable may pull the glider forward. Ready for takeoff is signaled by leveling the wings. Flags or paddles may also be used with an alternate set of ground launch signals.
Many gliders must be moved by hand or pulled by some type of tug to be relocated while on the ground. This often requires the assistance of individuals at the tips of the wings to stabilize the aircraft during movement. As you learn how, you should expect to assist in this stabilization for other pilots. This trade-off is required at some operations if you expect to continue using their sailplanes. Wing walkers are especially important during windy or gusty conditions. Someone to hold the tail may also be necessary while moving downwind or crosswind in these conditions. Most motor gliders have the advantage of being able to taxi, but the long wings require extra caution. If you are not sure that the wings will clear an object, it's better to shut the engine off and check rather than to find out with a resounding crunch. Wing walkers may be necessary even with a motor glider in very windy conditions. Radio communications are not always used at glider ports. The only radio available in the glider may be the handheld transceiver that you bring along with you. If your glider does not have a radio, it's highly recommended that you bring a handheld if your flight is originating or terminating at an airport with powered aircraft. You should make the appropriate radio calls on the Common Traffic Advisory frequency. This is a matter of safety and courtesy at non-towered airports. Non-powered gliders will often be staged off to the side of the runway to await a tow. At some operations, the staging occurs on the threshold of the runway. You should perform your before takeoff checks prior to hooking up for an aerotow or ground launch.
There are a number of mnemonic checklists used for this check. One uses the CB SIFT CB. You must also determine your emergency plan before giving the go-ahead for a hookup. Signal the ground crew when you're ready for hookup. For aero tow, the tow pilot will taxi past your position and the ground crew will hook up the tow rope and test the connection. The use of a tow hook in the nose of the glider is preferred on aero tow. The slack in the rope will be taken up by the tow pilot. Review your emergency plan again before signaling that you're ready for takeoff. Your wing runner will level your wings. As the tow plane accelerates down the runway, keep the wings level. You'll reach takeoff speed before the tow plane. Go ahead and lift off, but do not climb. Keep the glider flying low over the runway in ground effect. This will allow the tow plane to accelerate more quickly. Establish a crab is required to stay directly behind the tow plane. After the tow plane lifts off, you will establish a position behind the tug known as high tow. High tow is just above the tow plane's wake. Maintain this position behind the airplane as you climb. For a takeoff using a winch or auto tow, the ground crew will hook up the cable that has been pulled to your location. The preferred location for the tow hook on a ground-launched glider is near the center of gravity. In most gliders, the CG hook is on the belly of the glider just forward of the main landing gear wheel. This location decreases the stress on the glider and reduces control pressures. The hook must be designed to self-release if the sailplane overflies the winch or auto. This will help prevent the aircraft from being pulled down by the cable. The ground crewman signals for the slack to be taken up. When you're ready for takeoff, review your emergency plan and give the signal to launch. Track straight down the runway with your wings level until liftoff speed is achieved. Gradually increase the angle of your climb. Your pitch should be no higher than 15 degrees above the horizon at 50 feet, 30 degrees at 100 feet, and 45 degrees at 200 feet. This will allow you to lower the nose and prevent a stall if the cable or weak link should break. The before takeoff checks and emergency planning in a motor glider are similar to those in an airplane. Normal and crosswind takeoff procedures will also be similar if you have tricycle or conventional landing gear. Other techniques may be required if your motor glider has a single main landing gear wheel.
The basic aerodynamic principles of soaring flight are the same as powered airplanes. The application of these principles varies just a bit between these two types of aircraft. When flying with the motor running, the motor glider experiences the same four forces that influence an airplane. Thrust opposes drag, and lift opposes weight.
A glider on tow encounters similar forces, though the thrust provided by the tow line may not act along the longitudinal axis. Once the motor is shut off, or the glider is no longer on tow, there are only three forces. The force of thrust is taken away. Of the three remaining forces, the weight of the aircraft does not change. Gravity still pulls the glider toward the earth. Lift now performs the double duty of holding the sailplane up in the air and pulling it forward. The lift vector takes on a forward slant in a gliding pitch attitude. Drag, in the form of induced drag and parasite drag, opposes this forward and downward motion. This force vector is directly opposite of the direction of flight. Speaking of drag, you probably remember that induced drag is a byproduct of lift. The phenomenon known as ground effect is a reduction of induced drag as the airflow around the aircraft is disrupted by the ground. This produces improved performance as the wings get closer to the ground. Ground effect is a function of the wingspan. All other factors being equal, the longer the wingspan, the higher the effect becomes apparent. The long wingspan of a sailplane will tend to produce a more noticeable ground effect, something to remember during takeoffs and landings. Recall that the adverse yaw experienced while rolling into and out of turns is also related to induced drag. The additional lift on the wing being raised produces additional induced drag. The additional drag on the wing causes the aircraft to yaw toward the rising wing. Rudder application is required to counteract the yawing moment. The long wings of a sailplane exaggerate this yaw. Consider a wing to be like a lever arm in a weight and balance problem. The longer the arm, the greater the moment for a given weight or force. The increased induced drag, while it may be no more than the drag on an airplane, is acting on this longer arm. This creates a stronger yawing moment and may require additional rudder pressure. The need to actually use a reasonable amount of rudder in turns can be a challenge at first for airplane pilots who learned to fly in modern trainers.
Another long wing related difference is overbanking tendency. In a typical training airplane, overbanking doesn't become noticeable until the bank approaches 45 degrees. In a long-winged sailplane, this can become noticeable at as little as 15 degrees.
Overbanking occurs because the wing on the outside of the turn is moving faster through the air than the wing on the inside of the turn. The faster airspeed allows the outside wing to produce more lift than the inside wing. The additional lift on the outside wing, which is also the raised wing, causes this wing to try and raise even more, or overbank. To maintain a specified bank angle, the pilot must apply some aileron opposite the turn. This increases the angle of attack on the inside wing and decreases the angle of attack on the outside wing. When properly applied, the variation in angles of attack and wing speeds will counteract each other so that the lift is approximately equal on the two wings and a bank angle can be maintained. Even with the lift on both wings approximately equal in the turn, the sailplane may still tend to yaw a bit to the outside of the turn. While the induced drag is about equal for both wings, the parasite drag has increased for the faster wing, creating a yawing moment toward the outside of the turn. This must be counteracted with a bit of rudder toward the inside of the turn.
Remember that a bit of opposite aileron and inside rudder may be required, and you'll find yourself flying coordinated turns in no time.
I've never been one to collect ratings that I don't use, but I have always found it useful to fly a wide variety of aircraft. Why? Because flying different aircraft helps me better fly the airplanes that I fly every day. For example, flying seaplanes and helicopters requires a lot of concentration on your height above the surface. I can always make better landings in my airplane after some time spent with seaplanes and helicopters simply because I've tuned up my eyes to judge height with more precision. The same goes for airplanes with a tailwheel. We can just get away with more in a tricycle gear airplane, and after a few landings with a tailwheel, the old depth perception is improved. That's not the subject, though. We're talking about gliders and motor gliders here, and there's a lot you can learn flying these that'll help you flying regular airplanes. It'll give you a good brush up on the basics, too. Over the years, we've tended to reduce flying to a standard operation, by the numbers. That is good in most aircraft, but things are a little different in a glider. There you're as close to flying like a bird as it gets. There are numbers to abide by. The best airspeeds, for example, are critical for getting the most out of the aircraft. But there's also a lot of so-called feel to flying a glider. If it feels right and sounds right, it probably is right. Then there's that long wing with those ailerons way out there toward the tip. You know what I'm going to say next, but I'll say it anyway. A glider will quickly remind you why you prop your feet up on the rudder pedals. Until you make peace with the harmony between the rudder and the ailerons, you'll do a lot of lurching around. We learned a little about the coordinated use of the controls flying regular airplanes, but they just don't complain about poor technique like a glider does. Fly a glider a bit and the ball in your Cessna or whatever will stay a lot closer to the center. Another thing a glider or motor glider does is take all the mystery out of power-off landings. In a sense, every landing in a glider and every landing with a feathered prop in a motor glider is a forced landing. Do it right or else. Do it a few times and you'll build confidence in your ability to hit the spot. No, most of the airplanes that we fly don't glide like a glider. and most don't have spoilers, but that doesn't really matter. What does matter is our ability to manage the energy of altitude and airspeed and parlay that into a nice soft touchdown on the desired spot. The glider will teach us that whatever we fly, we had best know the gliding characteristics of the aircraft. A big Boeing was flown to fuel exhaustion a while back and was successfully force landed. You guessed it, the pilot was also into gliders or sailplanes. Finally, all of us who fly treasure the time aloft. It's independence at its best. Well, when you substitute the gentle sound of the air slipping by for the roar of an engine and the snarl of a propeller, it gets even better. The motor glider's an airplane when we take off, but once up we can turn it into a glider for enjoyment of the purest and most independent form of flight.
The object of flying on aerotow is to remain directly behind the tow plane at your desired vertical position.
High tow, as described previously, is the normal position while on tow. It is best to use the horizon as a reference for maintaining your desired sight picture for this location. If the horizon is obscured, or you are flying in a mountainous area, this may not be possible. To find the high tow position in this case, you can descend slowly until you find the top of the tow plane's wake. Ascend to smoother air above the wake and maintain this point relative to the tug. The low tow position is below the wake of the tow plane. This location is used for cross-country tows when the glider is being retrieved from a remote airport landing. Low tow allows a better view of the airplane while in cruise flight and provides more time to react to airspeed changes. When flying on aerotow, the glider must turn whenever the tug turns. You'll want to maintain the same arc of turn to prevent problems on the tow. Generally, you are in the correct high tow turning position if you can just see the side of the tow plane's fuselage on the inside of the turn. If you see too much, you are inside the arc and risk slowing down. If you don't see the correct side of the fuselage, you are outside of the arc and have the potential to slingshot around the turn. If you get out of position behind the tow plane, you will need to ease back into the proper spot. Trying to get back too abruptly can lead to an overshoot and oscillations. Don't forget, your glider has some momentum that you will need to compensate for as you approach the correct location. If you ever get out of position and lose sight of the tow plane, release immediately. Returning to the normal tow position too quickly after a slingshot turn or after getting too high on tow can induce rope slack. Sudden acceleration or deceleration of the tow plane can also induce slack. Severe rope slack can endanger you and the glider if not corrected. Slackline can be corrected by yawing the nose of the glider away from the bow of the line or through the careful use of spoilers. The nose should be realigned and the spoilers should be closed prior to the rope becoming taut. This will help to reduce the stress on the aircraft and line. During your training, your instructor will induce line slack and help you to learn to recover in a safe manner. You will also learn to fly in a box around the wake of the tow plane. Boxing the wake is a proficiency maneuver that shows you have full control of the glider while on aerotow. When you reach your desired altitude, it is time to release and soar off on your own. The release should only be done from the high tow position. Before grabbing the release handle, visually clear the airspace around and below the glider and tow plane. Then pull the release handle twice to help ensure a clean release. Watch for the rope to spring toward the tow plane and other signs that you are no longer on tow. In the U.S., when release has been assured, start a level turn to the right. The tow plane will turn toward the left and descend. Climbing out on a ground tow can be counterintuitive for the pilot of an airplane. When your climb is powered by a cable from the ground, you actually pull back on the control stick to speed up. The auto or winch powering the tow must have sufficient capacity to handle these pulls. If you are about to exceed the maximum placarded tow airspeed, you need to lower the nose to slow down. If there is a crosswind on Climbout, establish a crab angle to avoid drifting downwind of the runway centerline. As you approach the top of the climb, your rate of climb will decrease. When ready to release, lower the nose of the glider slightly to decrease the pressure on the tow hook and pull the release handle twice. Confirm the release visually before soaring away. Climb out in a motor glider is much like climb out in an airplane. You need to maintain the recommended climb airspeed, and you may be required to make engine control adjustments as you climb. Keep your eyes outside the cockpit as much as possible for collision avoidance. When ready to begin soaring, shut down and secure the engine. The motor glider may have the option of restarting the engine and climbing again if soaring conditions cannot be found.
With the engine turned off, or when off of tow, the motor glider and the non-powered glider are very similar in flight characteristics.
Gliding straight ahead is just a matter of determining the appropriate pitch attitude for the desired airspeed and setting the pitch trim for this configuration. There is no pitch versus power argument in a glider. Pitch for your airspeed. A point should be selected out in front of the aircraft, and coordinated aileron and rudder inputs should be used to maintain the position of the point. Roll into a turning glide using coordinated aileron and rudder. Don't forget about the adverse yaw and overbanking tendencies. Adjust the pitch and trim as required to maintain the desired airspeed in the turn. Turns to a heading can be performed by applying the compass error corrections learned during your private pilot training. Another method of performing these turns is to note your current heading while in a straight, unaccelerated glide. Determine the difference between the current heading and the desired heading and estimate where the nose of your glider will be pointing after the turn. Select a landmark in that direction and turn toward the landmark. Check the new heading after rolling out and see how close it is to the desired heading. Adjust as required. While our goal in flying a glider is to soar for extended periods in rising air, it's necessary to learn the various ways to control the descent of the glider in high and low drag configurations. These skills become especially critical in the traffic pattern. A descent in low drag configuration is generally used to extend the glide distance of the aircraft. This may be in poor lift conditions or between areas of lift. Speeds to be used in these conditions will be discussed later in this program. Low drag would indicate that all spoilers or brakes are closed and flaps are either up or slightly negative. The controls of the sailplane should be coordinated to glide at the appropriate speed with the fuselage streamlined to the relative wind. A descent in a high drag configuration is used to get the aircraft down more quickly. This may be to prevent overshooting a landing spot, to sequence with other landing traffic, or to get down in very strong lift. High drag configurations suggest the use of spoilers, speed brakes, high flap angles, or drogue chutes. They also suggest the use of forward and turning slips, which can be very effective in some aircraft.
The variometer works off a principle different than the diaphragm and controlled leak system found inside a VSI. With a vane-type variometer, there are two air ports. One port is connected to the static source. The other port is connected to an insulated reference chamber. The ports are on opposite sides of a vane inside the variometer. While in level flight, the pressure inside the reference chamber tank is the same as the pressure at the static source. If the aircraft begins a descent, the pressure at the static source increases. The air flows toward the reference chamber and moves the vane. The vane moves the needle on the variometer to show a descent. When the descent is arrested, the pressure in the chamber completes equalization with the static port, and a hairspring returns the vane to the neutral position. When the aircraft begins to climb, the pressure at the static source decreases. The higher pressure air in the reference chamber seeks to equalize and flows toward the static source. This flow moves the vane and the needle shows a climb. The sensitivity and accuracy of this instrument is dependent upon the proper adjustment of the hairspring that recenters the vane. There are also electric variometers that do not have any moving parts. These devices determine the rates of climbs or descents using the cooling effect of the airflow over two thermistors. Thermistors are devices which change their electrical resistance with changes in temperature. The variometer measures the difference in the resistance and indicates this as a rate of climb or descent. Variometers may have both visual and audible indications of the climb or descent. An audible indicator allows the pilot to interpret this instrument without looking inside the cockpit, an excellent enhancement for safety. A variometer will measure climbs and descents due to the vertical movement of the air mass as well as those resulting from a dive or a pull-up, also called a zoom. The climbs and descents that are of most interest to a glider pilot are those related to the vertical movement of the air. The indication resulting from a pull-up is often referred to as a stick thermal. Stick thermals may give the pilot the false impression of upwardly moving air, and it is desirable to eliminate these indications. A variometer with a total energy compensating system is designed to reduce the indication of stick thermals. Total energy systems sense the change in airspeed associated with a dive or a pull-up and adjust the indication of the variometer accordingly. A Venturi-based system modifies the pressure on the static source side of the variometer. An increase in airspeed will lower the pressure inside the Venturi. The lower pressure from the Venturi is introduced into the increased pressure from the static source to offset this increase in pressure. The resulting static source pressure delivered to the variometer has less change from the reference chamber and thus shows less indication. A decrease in airspeed increases the pressure from the Venturi to offset the decrease in the pressure from the static source. This also delivers a pressure to the variometer with less change from the reference chamber. Another type of compensated variometer is the netto, or air mass variometer. When calibrated correctly, the netto indicates the vertical speed of the air mass only. It does not indicate the vertical speed of the glider when descending in still air. This may be accomplished using a controlled leak in the pitot head or electronically. Accurate calibration of a netto system can be difficult.
Presenting what you should know about speed to fly is Bob Wander. Bob has been a glider flight instructor since 1980 and has accumulated over 7,000 glider flights. He has written several books on gliding, including portions of the FAA's Glider Flying Handbook, and is a regular contributor to Soaring magazine. A featured speaker at every American National Soaring Convention since 1989, Bob is also a recipient of the Soaring Society of America's National Exceptional Achievement Award.
When you were taught about gliding flight in an airplane after engine failure by your instructor, you were probably taught one simple airspeed. It was called the best glide airspeed. This airspeed has several other names: the maximum lift-to-drag ratio airspeed, the best L/D airspeed, or simply maximum gliding distance airspeed. This simple concept will not get you very far in gliding. In gliding, we need to study and master the concept called speed to fly.
Speed to fly describes the indicated airspeed that will provide the flattest glide for a given condition of convection. Horizontal wind speed does not matter for speed to fly. Only the vertical speed and direction are relevant. We determine the appropriate speed to fly using a graph called a glider polar. The polar is usually supplied by the glider manufacturer, but you can also create one yourself on a still day. To create a glider polar, the manufacturer determines the descent rate of the glider at various airspeeds in still air. The descent rate is plotted on the vertical axis of a graph and the airspeed on the horizontal axis. The dots are connected, and the resulting curve is considered to be the glider polar. To simplify the determination of glide ratios, or how far the glider will travel through the air horizontally for a given vertical descent, the units for both the vertical and horizontal speeds should be the same. In our examples, we use knots. The top of the curve is the airspeed with the lowest descent rate. This airspeed is the minimum sink airspeed for the sailplane. It is the speed that will keep your glider in the air for the longest period of time in still air. If we draw a line from the 0 point of the axes to any point on the curve, the glide ratio for that speed is the slope of the line. Divide the horizontal speed by the vertical speed to determine this slope. Most sloped lines will intersect the curve at 2 points. The glide ratio at these two speeds is the same. You will travel the same distance, but you will arrive there sooner at the faster speed. A line drawn from the 0 point and tangent to the curve is the flattest slope possible for an intersecting line. The tangent intersection is at the best L/d speed. The slope of the tangent is the best glide ratio that the sailplane is capable of in still air. In still air, best glide speed provides the flattest glide covering the most distance and is the speed to fly. In sinking air, the glider polar shifts downward by the magnitude of the descending air. This changes the point on the curve where the tangent intersects. The new speed to fly will be faster than the best glide speed. This gets you through the sinking air more quickly and provides the flattest glide possible for sinking conditions. Shifting the curve on your glider polar can be difficult. It is easier to shift the origin of the tangent line up from 0 by the vertical velocity of the sinking air. This will provide the same result as shifting the curve. In rising air, the same basic principle applies. This time, shift the origin of the tangent down from 0. The tangent ceases to be useful as the vertical velocity of the rising air exceeds the sink rate of your glider at minimum sink airspeed. When the air is rising faster, fly at the minimum sink airspeed.
Looking at speed-to-fly concepts for gliders, you might conclude that it would be difficult to do these calculations in flight. You'd be correct. It's best to do them before you fly, and then find a simple way to present the information you need on the panel of the glider. An easy way to do this is to have a speed-to-fly table that is attached to the instrument panel of the glider near the variometer. By looking at the sink rate showing on the variometer, you can then identify the appropriate speed to fly for that particular condition of sink. Set the pitch attitude of the aircraft to achieve that speed and you're on your way. It's important to note whether the variometer is an uncompensated variometer or a total energy compensated variometer. You can also mark the speeds around the edge of your variometer or purchase a rotatable speed ring for the variometer with the numbers on the dial. These generally work best with a total energy compensated variometer. For getting started, set the index for the ring at the 0 mark on the variometer. Other settings are often used by sailplane pilots in competitions who are pickier about the lift that they will utilize. The application of speed to fly will come into play as we begin discussing thermal soaring in a later segment. Speed to fly is not the only concept that uses the idea of the glider polar. When the soaring day is finished and you are gliding back towards your glider port, you need to compensate or adjust your gliding speed to take into account lift and sink currents and also horizontal wind currents. Determining the optimum airspeed to fly on final glide is affected by these headwinds or tailwinds.
When compensating for a headwind, shift the origin of our glider polar tangent line to the right and find the intersect point. You will see that a faster airspeed is required to maximize the distance covered with a headwind. This allows you to penetrate the headwind more readily and spend less time being influenced by its effects. If you find yourself in the double whammy of sinking air and a headwind, the origin of the tangent line gets shifted up and to the right, giving you a much higher final glide airspeed. With a tailwind, the origin of the tangent gets shifted to the left. This slows down your final glide speed to something less than your L/d max speed, giving the wind more time to help you along your way. Headwind and tailwind speeds can also be calculated and placed on a chart before your flight. These adjustments should be combined with the speed to fly adjustments for a total final glide adjustment.
There are also a number of calculators, manual and electronic, that can help you determine final glide airspeed for your glider. Here's a simple way to do it in the absence of calculators. Determine the headwind component. Then add half or 2/3 of that value to your calm air, best L/D airspeed in the glider being flown. That will be very close to the optimum value and will get you back to your home airport with maximum altitude.
Training maneuvers in a glider are much like the same maneuvers in an airplane. There are some factors to remember in a glider that might not be considered in an airplane. First, stay within gliding distance of a suitable airport or glider port. This is important even in a motor glider. Consider the engine to be an insurance policy, but don't count on it to start every time.
Second, a lot of altitude can be lost while performing these maneuvers, so start with plenty to spare. Third, recovery will be without the use of an engine. This is where much of the altitude loss can occur. As in an airplane, be sure to perform clearing turns prior to each maneuver. Much of the time spent soaring is spent at or near the minimum control airspeed. In many gliders, the minimum sink airspeed is within about 10 knots of stall speed. Because a lot of time is spent in this slower airspeed range, learning the low-speed handling characteristics of the glider being flown is imperative. For slow flight during the practical test, the glider pilot must establish and maintain the airspeed at which any further increase in angle of attack or change in configuration would result in a stall. This must be performed in straight and turning flight with various configurations and bank angles. The pilot is not expected to maintain altitude during this maneuver, and the pitch of the aircraft is the primary airspeed control. Heed the stall warning horn and any pre-stall buffet to avoid a stall during this maneuver.
Stalls in a glider are much like the power-off stalls in an airplane. The difference comes during recovery, as the application of power is not an option.
Set the appropriate configuration for the stall and begin to slowly pitch up. Warning signs of an approaching stall include the stick being back, the pitch attitude rising, the airspeed decaying, the wind noise decreasing, the controls becoming less responsive, and the pre-stall buffet. You may also hear a warning horn as you approach the stall. Finally, the stall brake will occur. Some aircraft, like the Extreme, have benign stall characteristics. With a gradual and coordinated entry into the stall, the Extreme tends to demonstrate a stall by full aft stick with a descent. The brake is not always apparent. Higher performance sailplanes may have much more aggressive stall characteristics. Recovery from the stall is initiated by decreasing the pitch attitude and rolling the wings level with coordinated use of aileron and rudder. The configuration is cleaned up and a glide is established. Stall recognition and recovery practice should be performed in clean and dirty configurations and in straight and turning flight.
Spins are not a required maneuver for the private and commercial practical tests, but stall spin awareness training is required. Spins during training or the check ride are required for the addition of a flight instructor certificate in the glider.
Some gliders are approved for spins, others are not. A spin is the result of a stall with a yawing moment. The wings must be stalled in order for the spin to occur. Lack of coordination at the stall brake may provide the yawing force that starts the spin rotation. If no manufacturer's recommendations are available for recovery, the following generic procedures may be helpful. Start by neutralizing the ailerons. Next, apply full rudder against the rotation, then reduce the angle of attack by briskly pushing the control stick forward. After rotation stops, neutralize the rudder and gently recover from the resulting dive to a normal glide attitude. During recovery, mind any airspeed limits for flaps, spoilers, or dive brakes. This procedure should be preceded by a power reduction to idle in a motor glider with the engine operating. Steep turns in a glider are important maneuvers and indicative of the pilot's skill at handling the aircraft. You will use them when working lift as well as for certain emergency maneuvers. For your practical test, steep turns will be performed at 45 degrees of bank. Unlike an airplane, maintaining altitude is not a requirement. The bank angle and airspeed do have performance criteria. Establish your target airspeed and find a prominent landmark to use as a start point. Gradually roll into the steep turn with a coordinated use of aileron and rudder. Apply sufficient back pressure on the stick to maintain your desired airspeed. Once established in the turn, use opposite aileron and inside rudder to maintain coordination. A slight adjustment of the trim control may also be helpful. If you start to pick up speed, apply additional back pressure to raise the nose. You may also need to shallow the bank slightly to prevent entry into a steep spiral. Maintain your bank angle and airspeed until approximately 25 degrees before your desired rollout heading. Roll out using coordinated aileron and rudder, and release the additional back pressure to prevent ballooning. If you added trim, you may have to apply some forward pressure on rollout. Re-establish a straight glide and trim for this configuration.
One common error when performing steep turns is allowing the turn to slip into a steep spiral. This can occur if the turn is uncoordinated and the bank gets too steep.
The nose of the glider falls and it begins to pick up excess airspeed. In attempting to recover, the pilot applies back pressure. The steepness of the turn does not allow the nose to be raised. The back pressure only tightens the turn. The excess airspeed increases the overbanking forces and the nose falls further. This cycle can progress quickly, and because gliders have such low drag, the speed can rapidly increase past VNE. The rapid progression and increased forces result in the structure of the glider being overstressed. The proper recovery from a steep spiral is to roll the wings level first, then raise the nose to normal gliding flight, taking care not to overstress the airframe.
Convective currents are localized vertical air movements, both ascending and descending. For every rising current, there is a corresponding descending current. Downward moving currents frequently occupy a larger geographical area than do upward moving currents. As a result, the upward moving currents tend to have a higher velocity than do the downward moving currents.
The sun heats the surface of the Earth. Convective currents are created when the various surfaces heat at different rates. This variation depends on a number of factors, including the color, material, and moisture content of the surface. A thermal is the updraft found in a small-scale convective current. About 80% of all soaring in the United States depends upon thermal lift. Thermals are often considered to be steady columns of rising air, but the truth is that they come in many shapes and sizes. The surface creating the thermal, the speed and the direction of the wind, and the angle and intensity of the sun all conspire to create thermals with irregular, non-cylindrical shapes. When an area heats quickly, the thermal may have a column form. If the surface heats more slowly, intermittent bubbles of rising air may occur. Light to moderate winds will cause the thermal to rise at an angle. Strong winds, or wind shear, will distort weak thermals and make them unusable. Wind shear may also sever a strong thermal before it reaches its full potential.
Thermals may continue for a long lifetime, or they may dissipate very quickly. Finding and using these rising columns of air is a very large part of the enjoyment of the sport of soaring.
One sign of thermal production can easily be seen on days when the air is moist. Growing, fair-weather cumulus clouds on a sunny day indicate the presence of convection and the potential for thermal soaring. Cumulus clouds follow a life cycle that can be recognized by the shape and activity of the cloud. As a soaring pilot, you are looking for cumulus clouds that are in the growth stage. Developing cumulus clouds have a concave base as the stronger center of the thermal pushes the moist air up into the cloud. The edges of the cloud are also inclined to be more sharp and defined. You may also see these edges rolling upwards. Remember that thermal angling that we spoke of? This suggests that you will most likely find the strongest portion of the thermal under a building cumulus on the upwind side of the cloud. How far upwind depends upon the strength of the winds aloft and how far you are below the base of the cloud. A dissipating cumulus cloud will have a more convex or rounded underside, and the edges will be ragged and less defined. When the air is dry, clouds will not develop even though thermals may be present. You need to look for other signs of convective activity on these days. Knowing what type of surface is likely to produce a thermal is the first consideration when searching on a dry day. barren, sandy, or rocky surfaces, plowed fields, stubble fields surrounded by green vegetation, cities, factories, and large parking lots are often good sources of rising heat. The angle of the sun affects the location of thermals in hilly areas. The morning sun will heat the eastern slopes, the midday sun will heat the southern slopes in the northern hemisphere, and the afternoon sun will heat the western slopes. This changes the location of the rising air throughout the day. Dust and smoke may also be useful in your search for thermal activity. As heat causes the air to rise, cooler air flows over the heat source to replace the rising air. Dust or smoke converging on a suspected thermal generator is a good sign that the air is rising. Divergent dust or smoke indicates that a thermal is not being produced. Dust devils indicate the presence of a strong thermal. Dust devils are whirling winds that look like mini tornadoes and are typical over sandy or dusty dry surfaces. These thermals can be strong and turbulent. You will want to circle around the dust devil, generally in the direction opposite of its rotation, and keep the wings of your glider out of the actual dust column. This will keep you out of the most severe turbulence. Another sign of thermals on a clear day is the presence of soaring birds. Birds have an uncanny knack for finding rising air.
Finally, if other sailplanes are in the area, you may be able to catch a ride in the same thermal lift that they are using. Now that you've found the lift, what we do next is work the lift. This is using the thermal in order to climb rapidly.
As you will recall, the speed to fly in rising air is your minimum sink airspeed. This should be corrected for the G load being sustained in the thermaling turn. In a 45-degree banked turn, the G load is 1.4, and the speed increase factor would be 1.2, the square root of the increase in G load. You should slow to this speed while working a thermal. One of the keys to thermaling is the ability to maintain a constant pitch attitude and bank angle with good coordination. This is where your practice in slow flight and steep turns will come into play. Gliding along at your appropriate speed to fly in the area where you expect to find a thermal, you may notice an increase in your sink rate just prior to entering a thermal. This will be followed by an upward motion that you will feel in the seat of your pants before it shows up on your variometer. If you wait for the vario to peak before attempting a turn into the thermal, you may miss the core of strongest lift. While sensitive, variometers still exhibit some lag. You will need to turn and circle to work most thermals. If another glider is already working the lift, you must make your turns in the same direction. The first glider into the thermal determines the direction of turns. If no other gliders are present, and you felt one wing lifting more quickly upon thermal entry, turn toward that wing. This will make your turn most likely toward the thermal core. If neither wing seem to lift more, the choice for turn direction is yours. Upon turning into the thermal, you must judge if you made the correct choice. Does the variometer show a nice climb, or are you now back into the sink? If you see a climb, congratulations! You most likely turned in the correct direction. Continue this turn and monitor your rate of climb. If, on the other hand, you experience an almost immediate sink, you probably went the wrong way. Not to worry, you can fix this. Keep turning the glider in the same direction for about 270 degrees of turn. Level your wings for 3 to 5 seconds or until you feel the lift again. Turn back into the lift using the original direction of turn. This 270-degree centering correction should put you into the lift on approximately the same path as you would have had by turning the other direction in the first place.
Now that we are circling in a thermal, fly the glider with constant pitch attitude and constant bank angle to fly round circles in the sky. Pay attention to the variometer and note the side of the circle that has the strongest lift, the fastest rate of climb. Shift your circle in that direction to achieve the fastest possible rate of climb in that particular thermal.
If you are circling to the left and you find that the lift is strongest on the east side of your circle, heading north, and the weakest is on the west side of your circle, heading south, try leveling your wings momentarily on a heading of east, then rolling back into your turn. This should shift your position slightly to the east and hopefully into stronger lift. Monitor the trends in this new circle. Continue making centering adjustments until you have the maximum rate of climb possible throughout the circle. Realize that some thermals may be too small to stay inside, regardless of your centering skills. Also, thermals will dissipate over time or with an increase in altitude. You need to learn when to quit chasing a particular thermal and move on to the next. This comes with practice and guidance from your instructor. While thermaling, even when monitoring the variometer, be sure to keep your eyes outside of the cockpit for the majority of the time. You do not want to bust a cloud clearance minimum or have a close encounter with another aircraft.
There are some fundamental differences when approaching to land in a glider versus an airplane. First, you will most likely be in a continuous descent throughout the traffic pattern when flying a glider. It is generally considered inappropriate to work lift when in the traffic pattern. You can slow to minimum sink as you pass through the lift for a bit of extra altitude, but continue toward your landing.
The traffic pattern for a glider is different than an airplane. The so-called 747 patterns flown by some fixed-wing pilots will almost guarantee an off-airport landing for a glider. At some airports, glider traffic patterns are flown on the opposite side of the runway from airplane patterns. At other airports, glider patterns are on the same side of the runway but kept closer to the landing area. The goal of the glider traffic pattern is to assure a safe landing on the intended spot. The glider pilot must be willing to depart from the standard traffic pattern as necessary to achieve this goal, given the fact that there will be no go-arounds. The rectangular traffic pattern described in the Aeronautical Information Manual for propeller-driven aircraft is not always consistent with this goal.
The glider traffic pattern that we will be discussing in this program is known as the safe landing cone. The safe landing cone is an area of airspace that comes to a point in the landing area.
In a no-wind condition, the glider will follow a particular flight path in the clean configuration. This glide angle defines your absolute flattest glide, and you must never get below this flight path on final approach. You must also learn to recognize when you have broken this cardinal rule, as it will indicate the need to go to Plan B. The bottom of your safe landing cone must be above this angle to allow for varying conditions and for some margin of error. With addition of wind, the angle of this minimum approach path will change. A headwind component will make it steeper. Always have a good idea of the wind speed and direction while flying in a glider, and be ready for it to change. The glider will also have a maximum descent angle with all mechanical drag devices fully deployed. For the purposes of planning your approach, assume that this angle is not using slips or any unusual maneuvers. This is the top of your safe landing cone. You will want to plan your approach so that you remain between the minimum and maximum approach angles at all times. Often, this means a good stabilized approach will require the partial deployment of the drag devices. This allows you to close the devices to flatten the approach and fully open the devices to steepen the approach. The safe landing cone traffic pattern is entered from an initial pattern entry point. The initial point is generally a prominent landmark located on the downwind side of the traffic pattern, near the pattern, but not in it. The point is such that flying from the point will allow a 45-degree entry leg to the downwind, joining the downwind at a location appropriate for the runway. The initial point should be located so that passing over it at approximately 1,000 feet AGL allows the pilot to enter and fly a safe landing cone to touchdown. The pilot should approach the airport by aiming for the initial pattern entry point. The pilot should adjust his flight path to ensure flying over the point at 1,000 feet AGL. If circling is required to lose altitude, this should be completed prior to reaching the initial point. For a left-hand traffic pattern, circling to the right will allow the pilot to clear the downwind leg of the pattern before turning in on the entry leg. The entry leg is considered to be the flight from the initial point to the downwind leg.
A pre-landing checklist should be completed prior to the entry leg. Since most of our students here at Sporty's Academy are already fixed-wing pilots and the Extreme has an engine, we use an adaptation of the classic Gump's checklist.
We also add a popular checklist in gliders using the acronym FOO STAL to round out the before landing check. Upon entering the downwind leg, the pilot must judge his relationship to the runway and adjust as required. The pilot must learn to estimate the angle between the horizon and the landing area. This angle is sometimes referred to as the dip angle. In many gliders with reasonable performance, the dip angle is typically 25 degrees in calm conditions. This will vary with glider performance and in convective and windy conditions. On each subsequent leg of the traffic pattern, the pilot must continue to ask, "Is my dip angle correct?" On the downwind leg and abeam the touchdown point, the glider pilot should make a slight turn toward the runway. This is sometimes referred to by glider pilots as the diagonal leg. It keeps the aircraft close to the landing area and provides a better view of the runway. The angle used for the diagonal may vary based on the aircraft and conditions. The turn to base leg is initiated when the touchdown point is approximately 45 degrees behind the wing minus the angle used for the diagonal leg. The turn to final should be initiated so the aircraft rolls out with the appropriate crab angle and on the extended runway centerline. On final approach, the pilot must continue to judge the relationship of the approach path to the safe landing cone. The pitch of the aircraft should be used to maintain the appropriate airspeed. The flight path should be adjusted by the application or removal of drag devices such as the spoilers. Remember that excessive speed or diving at the runway may cause extensive float when the glider enters ground effect. The flare must be initiated at the appropriate altitude for the glider that is being flown. Hold the aircraft just off the ground and let it settle gently to the runway. Properly planned and executed, you should be able to exit the runway before you stop rolling. This allows the next aircraft to have a clear landing area. After clearing the runway, perform your after-landing checklist. In a motor glider, you may be able to restart the engine and taxi as needed. Without a motor, you'll need a tug or the help of a few friends to get to your destination on the airport.
Under ideal conditions, the traffic pattern will have a familiar appearance. Strong wind conditions or a miscalculation may require some adjustment. If you find yourself approaching on a windy day or too low on downwind, you may be required to make an earlier turn to base to get back into your safe landing cone.
Remember, one of the worst places that you can be in a glider is too low. A misjudgment in this respect may mean that you won't be landing on the runway as planned. If you find yourself too high on the base leg, use a combination of speed brakes and slips as required to bring your aircraft to the appropriate altitude. If you do find yourself too low on the base leg, it becomes major decision time. Can you get back into your safe landing cone and make the runway, or do you need to land in an alternate location? Do not try to stretch a glide by raising the nose of the glider. Think about the glide polar for your aircraft. If you're already at the best glide speed of L/D max, raising the nose will only increase your angle of descent and bring you closer to a stall. Another mistake in this realm of flight is trying to quicken a turn to final by overusing the rudder. An uncoordinated turn coupled with trying to stretch a glide by raising the nose sets the aircraft up for the classic stall spin accident. It may be possible to salvage a low pattern situation and land on the runway. The key is to streamline the glider by closing all speed brakes and maintaining coordinated flight at the best glide speed for the wind conditions. Proper coordination and attitude in the turns is crucial to the success of the outcome. The pilot may also need to proceed directly to the landing point to get back into the safe landing cone. This shorter distance may allow a successful landing. Always have an alternate plan in mind, just in case it isn't enough. Your speed on final should be the speed recommended by the manufacturer. In many gliders, this is the L/D max speed. If the wind is blowing, increasing your speed by half of the headwind component on final will allow you to penetrate the wind and get further than the no-wind best glide speed. In gusty conditions, you should also increase your speed by 1/2 of the gust factor. Remember that you will have to bleed all of this extra speed back off during your landing flare. Crosswinds must also be corrected. This will mean using a wing-low side slip to counteract the drift, or kicking out of a crab angle at the point of touchdown. When using the side slip method, remember that sailplanes have long and low wings. Be certain that the bank required for the side slip will not exceed the clearance for the wing.
Many gliders do not have a radio because they do not have an electrical system. There is no doubt that radio communication can enhance safety. For this reason, if your glider is equipped with a radio or you have a handheld, it is highly recommended that you use it. This is especially important when flying at an airport with powered aircraft. Radio calls should be used to announce approaching and entering the traffic pattern. Ensure that other traffic in the pattern understands that you are flying a glider. A glider or motor glider has the right of way over an airship, airplane, or rotorcraft. Of course, an aircraft in distress has the right of way over any other aircraft. When dealing with other aircraft, do not assume that they will give up the right of way to you. The other aircraft may not see you or may not realize that you are flying a glider, especially if one of you isn't using a radio. Always fly defensively. It is better to land safely away from the airport than to try and force the right of way and cause a collision. When approaching an airport in a motor glider with the engine operating, the traffic pattern can be flown and the maneuverability is like that of an airplane. Here at Sporty's Academy, we encourage our glider pilots to blend in with the flow of fixed-wing traffic when the engine is running. While a motor glider legally has the same right-of-way as any other glider, we have found that not pushing for the right-of-way makes for a much better opinion of the glider program here. When approaching the airport with the motor secured, we communicate this fact clearly and request the right-of-way to the active runway. We even change our call sign from Extreme Motor Glider 6 Tango Charlie to Extreme Glider 6 Tango Charlie. We add the motor glider or glider description for the benefit of pilots who are unfamiliar with models of gliders. We also add negative engine to the end of our radio transmission while in soaring mode to make it clear to other pilots that we would like the right of way. A little common courtesy and communication can go a long way.
In the traffic pattern segment, we discussed normal and crosswind landings. In this segment, we'll look at some other types of landings. When things aren't going right on approach in an airplane, you can always go around. In a glider, this is not an option.
The only exception to this rule is when you are landing a motor glider with the engine running. You might do this after a cross-country in poor lift conditions or when simulating soaring mode for the purpose of improving your landings. Performing a go-around in a running motor glider is much like performing a go-around in an airplane. The primary difference is the air brakes versus the flaps. With flaps, you generally apply power for the go-around and gradually raise the flaps as your climb permits. This is because raising the flaps quickly causes a reduction in lift along with the reduction in drag. Settling of the aircraft may result. With air brakes or spoilers, you are increasing the lift and reducing the drag when you close them. You should close these prior to applying power for the go-around. This allows you to concentrate on flying the motor glider during the go-around. After applying power, pitch for the climb attitude that will produce the desired climb airspeed. As with any go-around, adjust your course slightly to the right so that you can see the runway and other traffic. When we discussed approach angles, we indicated that for planning purposes, you should only consider the use of normal drag devices. You do have another option to increase the maximum angle of descent in most gliders when actually flying the approach. You can use a forward slip to get your glider down much more quickly. As in an airplane, the forward slip is entered by banking the glider and applying opposite rudder. Depending on the design and location of your pitot tube and static ports, your airspeed indication may not be accurate in this configuration. You need to know and fly your normal approach pitch. Do not let the nose of the glider pitch up, as this could lead to a cross-controlled stall. Allowing the nose to get too low can lead to excess energy upon recovery. This will likely cause the glider to float during the flare. You should understand and explore the forward, side, and turning slip characteristics of your glider with your instructor at a higher altitude before trying them in the traffic pattern. This exploration should include operations in various air brake and flap configurations. While the forward slip is useful on any approach that gets a bit high, it is especially important when landing the glider without the use of the spoilers.
Failure of the mechanical spoilers is rare, but it is important to learn how to land in this condition. In some sailplanes, landing without spoilers can be a challenge. To fly a somewhat normal glider pattern, use a slight forward slip in place of partial spoilers.
You will need to continue the slip while in turns. A turning slip should be performed such that the bank angle is toward the desired direction of the turn and used to control the rate of turn. The rudder is applied away from the turn. The rate of descent during a turning slip will be higher than a straightforward slip. Do not perform a turning slip by trying to turn with the inside rudder. This is a skid and can more easily lead to a spin. Maintain the appropriate pitch attitude for an approach and vary the forward slip to control your rate and angle of descent. Be prepared to float during the landing. Remember that the practice of this is a training maneuver. If your ability to get down to the runway is ever in doubt, use the spoilers to help make a safe landing. A landing that is not normally practiced in airplanes is required in glider training. This is the intentional downwind landing. A downwind landing may result if proper planning is not used when returning to the airport or glider port. The pilot may be trying to stretch a glide back to the airfield and using the wind to push him along. The pilot reaches the airport but does not have sufficient altitude to fly the traffic pattern and make a landing into the wind. Another possibility is a premature termination of the tow or a motor glider engine failure before the glider has reached an altitude adequate for flying the traffic pattern. In this case, the pilot must make a quick and coordinated turn to return to the runway. Never a good feeling at a low altitude. For safety, the instructor or flight school should have a wind limitation for the intentional practice of downwind landings. The intentional practice of this maneuver should also only be done with a qualified instructor on board. When landing downwind, speed control is critical. Maintain the normal recommended approach airspeed during your approach. You may need to use full spoilers and a forward slip to attain the correct approach angle. The wind will be pushing you along, and the high ground speed may fool you into flying at too slow an airspeed. Try to touch down in the first third of the runway. Anticipate that you may float significantly. Communication is a key requirement to practicing the downwind landing. The traffic pattern should be clear, and everyone in the area, including the tow pilot, should be aware of your intention to practice this maneuver. At touchdown, you will be traveling at a higher ground speed than normal. Apply brakes as necessary and maintain the runway centerline until you are slow enough to safely turn off. Keep in mind that in sailplanes without differential wheel braking, the effect of the rudder will reverse when you slow to a ground speed less than the tailwind that is blowing behind you. This can be a significant concern when landing with a strong tailwind.
While you will learn and practice this maneuver, proper pre-flight inspection of the aircraft and tow rope, along with conservative planning and execution of the flight, should make all of your downwind landings practice only. There are many emergency situations that can occur in gliders regardless of the launch method. Some are launch method or aircraft specific. When training in a motor glider, like the Extreme, you'll need to learn how to react to engine problems in addition to other glider emergencies.
On aero tow, you need to be concerned about the health of the tow plane and the rope. With ground tow, the power-producing capability of the winch or auto, along with the condition of the cable and weak links, are of concern. Prior to any takeoff, you need to determine the wind strength and direction. You must also determine your return decision altitude and plan the direction that you will turn for the existing conditions. As with all types of flying, you should be prepared for the engine to fail. Or in the case of a non-powered glider, you should be ready if the tow line breaks or the tow otherwise terminates prematurely. In airplanes, we are taught not to attempt a return to the airport unless we have gained 500 to 1,000 feet of altitude, depending on the airplane, if the engine quits after takeoff. In gliders, you may find that this recommended altitude is lower. The Pilot's Operating Handbook for the HK36TC recommends that landings be made straight ahead if the engine fails below 280 feet. Above this altitude, other options may be available. If the engine fails or the tow terminates prior to reaching a return decision altitude, you should land straight ahead or within a few degrees of the extended runway center line. Time permitting, try turning on the electric fuel pump if one is installed prior to securing the aircraft for touchdown. This might save you an off-airport landing. Secure the aircraft and execute an emergency landing as required. Don't forget that it is more important to fly the glider than to run through any emergency checklists at this low altitude. You may have only a few seconds until you touch down.
If the engine fails or the tow line breaks above your return decision altitude, you'll need to react quickly to return to the airport.
This maneuver is the same for an engine failure in a motor glider or a premature termination of the tow, a PT3 in glider speak in an unpowered glider. It should only be practiced with an experienced instructor on board the aircraft. If there are no obstacles, you should turn into a crosswind so that it will help to blow you back toward the runway center line while turning. The procedure calls for lowering the nose to the best glide attitude and rolling into a coordinated 45-degree bank in the predetermined direction. A 45-degree bank is considered to be the most efficient bank angle to use for this maneuver. It provides the fastest rate of turn for the amount of altitude lost. Always remember that flying the glider is your first priority. Complete the memory items on your checklist if time permits and prepare the aircraft for a downwind landing. Depending on the wind conditions, the turn for your course reversal will likely exceed 180 degrees. This allows you to return to the extended runway center line. A turn in the opposite direction will be required to keep you there. If you get too low, consider other open areas besides the runway. A taxiway or an open field landing is preferable to digging in a wingtip trying to get back to the runway.
The next emergency altitude to consider is the pattern decision altitude. You should be able to fly a modified glider traffic pattern from this altitude and return to the runway from which you took off. In this case, your landing is back into the wind.
If you have a PT3 or engine failure above your pattern decision altitude, turn the glider and fly as normal a traffic pattern as possible. Remember your safe landing cone and stay in it until you touch down. If given the signal to release by the tow pilot, do not try to figure out why. Quickly clear your airspace and release. Follow the emergency plan for your altitude. Do not release if the tow pilot is just giving you an air brakes open signal. Close your air brakes or otherwise determine what the problem the tug pilot is trying to communicate. If the brakes are open and you release, your glide ratio will not be as expected and your decision altitudes may be worthless. If you are unable to release from an aero tow, signal the tow pilot. He will release his end of the line after flying you back over the glider port. Expect the tow plane end of the tow line to spring toward you when this occurs. Plan your approach to landing a bit higher than normal to prevent snagging the dangling line on an obstacle. If the tow pilot cannot release his end of the rope, you must land together. You should maneuver to the low tow position for the descent and landing. The tow pilot should fly a slightly higher approach than normal, and you should touch down before the tow plane does. Do not use any wheel brakes until after the tug is on the ground. If you are unable to release from a ground tow, maneuver over the winch to attempt to activate the automatic release feature. If you feel yourself being pulled down and it does not release, enter a steep turn over the winch. The ground crew should sever the cable. Try to land in an unobstructed area to avoid snagging the cable. Under or overspeed conditions on a ground tow should first be corrected using the pitch. If this is unsuccessful, release and follow your PT3 emergency plan. If you experience porpoising or pitch oscillations while on a ground tow, relax the back pressure on the stick to shallow your climb. You can slightly steepen the climb again after the oscillations stop. This problem is more common when using a nose hook for a ground tow instead of the recommended CG hook. Other power plant related emergencies may also occur in a motor glider. You may be unable to restart the power plant in the normal manner. In the extreme, the engine is normally restarted using the starter. After extended soaring flight, the battery may not have enough power to turn the engine over. In this case, a descent is entered to gain speed. The propeller is taken out of the feather position and windmilled to start the engine. Problems may also occur with the propeller feathering mechanism or the engine stowing or unstowing device. Gliding flight with the engine unsecured will add a significant amount of drag.
Inadvertent flight into instrument meteorological conditions can be very dangerous because most gliders don't have gyros. If IMC is encountered, deploying the spoilers and speed brakes may keep your speed from becoming excessive and allow you to descend into visual conditions safely.
Unlike the pilot of an airplane, the pilot of a glider or a motor glider with a secured engine does not have the option of performing a go-around when an approach to landing doesn't go correctly. You must always have an emergency plan or two in mind during this critical phase of flight. The incursion of an aircraft, vehicle, or animal on the landing runway can be a true emergency in a glider. The only way to prepare for this event is to have alternate landing areas in mind from the time you approach the traffic pattern. As you glide lower on final approach, your alternatives will decrease, but you may still have options. Consider taxiways or grassy areas on the airport as an option. Would it make more sense to land short of the runway or extra long? Review your options until you are safely down on the ground and off the runway. After landing, make sure you do not become an obstacle for someone else. An off-airport landing, also called landing out, is more commonplace in gliders than in airplanes. This can happen if the engine on a motor glider fails to restart, if the pilot of any glider loses track of his location or altitude, if the glider encounters unexpected sink, or if the pilot tries to stretch a glide and doesn't quite make it back home. It's better to land under control in a good field than to try and stretch the glide and run out of landing options.
If you'd like to learn more about off-airport landings, check out one of the excellent motor glider-based courses on this subject around the country. These courses make use of the motor glider's ability to go around and allow you to make multiple practice approaches into different types of fields without the need for an aircraft recovery. An afternoon in one of these courses can help you develop more off-field planning experience than several years of gliding.
While about 80% of soaring depends on thermals, other phenomena can also provide the upward mobility needed. Let's take a basic look at some other sources of lift.
Upward deflection of the wind when it strikes a hillside is known as orographic lifting. This is the type of lift used when practicing ridge or slope soaring. Wide, continuous slopes with a moderate incline provide the best orographic lifting. Shallow slopes do not deflect the wind enough, and steep or rugged slopes create turbulent eddies that disrupt the lift. The wind must be within 30 to 40 degrees of perpendicular to the hill and should have a sustained speed of 15 knots or better to support a glider. The altitude of the usable lift can reach 2 to 3 times the height of the rise from the valley floor to the crest of the ridge. The rising air will be found on the upwind side of the slope. Flying on the downwind side of the ridge can be detrimental because the downward moving air and turbulence predominate on the downwind or lee side of the crest. To most effectively utilize the orographic lift, you must fly your sailplane parallel to the ridge or slope. This will require a crosswind correction to prevent spilling over the crest and into the sinking air. There are a few generally accepted practices used by glider pilots flying in ridge lift in the United States. Other than the issues related to right-of-way, these are not federal regulations. Be sure to check with your local glider port operator for any local variations on these or to determine the procedures used when flying outside the United States. First, never fly over or under another sailplane. You may be unable to see the other aircraft, or the pilot of that glider may be unable to see you. Second, when overtaking a slower glider, pass the aircraft by shifting your flight path toward the ridge. While this operation can appear to conflict with the alter course to the right requirement of Part 91, there is a good reason for this, which will be discussed in a moment. The glider being overtaken does have the right of way. The reason for shifting toward the ridge to pass, in the third ridge soaring practice, is that all 180-degree turns should be made away from the ridge and into the wind. This helps prevent the wind from blowing the aircraft into the ridge or over the crest while the turn is being executed. With all 180-degree turns away from the ridge, overtaking a slower glider on the ridge side assists in the avoidance of collisions. The fourth generally accepted practice is also a federal regulation. When two gliders approach head-on, both should alter course to the right to avoid a collision. The variation on this regulation in ridge soaring is that the aircraft shifting away from the ridge may have to shift further. The sailplane altering course toward the ridge may not have enough room to complete the maneuver safely. Another wind-related source of lift is the mountain wave. Waves can be produced on the lee side of a mountain when a stable stream of air is disturbed by the mountain. Wind at the summit must be greater than 15 to 25 knots, depending on the height of the range, and should increase at higher altitudes. The wind must be blowing within 30 degrees perpendicular to the mountain and remain approximately the same direction with increasing altitude to sustain the wave. Climbs to over 35,000 feet have been recorded in mountain waves. Wave crests are marked by lenticular clouds when sufficient moisture is present in the atmosphere. Rotors with the potential to produce severe or extreme turbulence are generally present below the crest of the waves. If sufficient moisture is present in the air, clouds resembling long bands of stratocumulus may mark the position of the rotors. Entry into the rising air of the wave is often detected by the uncanny smoothness of the air and a sustained rate of climb. You can attempt to maintain the wave by turning into the wind. If conditions are right, you will be treated to an elevator-like ride nearly straight up. Frontal lift may be available as warm air is forced aloft by colder air during frontal passage. This lift can be strong, but it is transitory. It can be difficult to find and use for extended flights. Other lift may be available when smaller air masses collide. Utilizing this phenomenon is known as shear line soaring. Sea breeze fronts are a type of shear line. These are created near the shore of large bodies of water as cooler air from the water moves on shore and displaces the warmer air over the land. The warmer air is lifted to create a ridge of rising air. Depending on the conditions, this ridge may be over the shore or as much as 150 miles inland. The wind produced by strong pressure gradients can disrupt the sea breeze effect.
Like all aircraft, gliders must fly within the national airspace system. Restrictions defined for special use airspace also apply to gliders. Gliders are relieved of certain equipment requirements for some types of airspace. For instance, a glider is not required to have a Mode C transponder when flying within 30 nautical miles of a Class Bravo primary airport, provided that the operations are lower than the Class Bravo ceiling and below 10,000 feet MSL. A transponder is also not required when a glider is flying above 10,000 feet MSL in other airspace. A transponder is required to fly over or into Class Bravo or Charlie airspace. An IFR-equipped aircraft and clearance are normally required to operate in Class Alpha airspace. In some cases, glider operations have been able to obtain a clearance to operate in a wave window into the Class Alpha airspace. A wave window is a geographically defined area up through the Class Alpha. A glider may fly inside the window, allowing the glider to climb higher than 18,000 feet MSL without needing specific clearance or the normal IFR equipment. Air traffic control will route all IFR traffic in the Class Alpha airspace around the window.
We hope you've enjoyed this introduction to gliding as much as we've enjoyed making it. Once you've mastered the basics presented in this program, a whole new world of learning will open up to you.
You might want to expand your soaring to include cross-country flying. You can work your way through the Soaring Society's ABC badges as you learn these important skills. Your glider port may have a higher performance or a single-seat sailplane that you can move up to after you've mastered the training gliders. You might want to check out or participate in one of the many soaring contests held around the country. You should be able to find a contest that is geared toward your skill level and aircraft in your area. As you advance in equipment and skills, you can step up to the next level of competition. If you'd like to find out more about gliders and soaring, take a look at any of the excellent books on the subject available from Sporties, including several topics written or edited by glider instructor Bob Wander. You'll be glad that you did.
For Bob Wander, Dick Collins, and all of us here at Sporties Academy, I'm Rob Ryder. So long.
The Soaring Society of America, or SSA, has been promoting soaring since 1932. The organization was originally formed to hold a national soaring contest each year. Today, the SSA does much more. The Soaring Society is dedicated to flight training and safety, promoting technological research and development, sponsorship and monitoring of competition, and representing the interests of gliding before government agencies. The SSA works diligently to preserve glider access to airspace across the country. The SSA is comprised of over 16,000 members with a mostly volunteer group of leaders. A small full-time staff is headquartered in Hobbs, New Mexico. These dedicated professionals manage the day-to-day business operations and publish Soaring Magazine each month. They also maintain the Society's website. An annual SSA membership meeting and convention provides an opportunity to learn about the latest advances in the sport of soaring and review the progress and plans of the organization. This is also a time to catch up with old friends and meet new ones. As the national organization for soaring activities, the SSA acts as a central information source for people interested in learning about the sport. The SSA also developed the ABC Badge Program, which provides standards for soaring achievements and training progress. The program is administered by a network of SSA instructors who ensure that the requirements have been met and issue these badges. The more advanced and internationally recognized badges of the Fédération Aéronautique Internationale, or FAI, in Paris, are also administered in the United States by the SSA. The Soaring Society has a number of affiliates and divisions. These groups, such as the Auxiliary Powered Sailplane Association, the National Soaring Museum, and the Sailplane Home Builders Association, provide members with additional resources for particular interests. The Soaring Society of America promotes the development of local clubs and chapters to better meet the needs of the individual glider pilot.